In this proof I'm going to need to use the fact that e to the x can be written as an infinite series 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x 4 plus 1 blah 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 forever. So either A, just accept that that's true, or B, go back to the C3 section and watch the proof that you can write e to the x in that way. So let's use the definition of the mean of a discrete random variable, because after all, the Poisson distribution is a discrete variable. X can take the values 0, 1, 2, 3, 4, etc, etc, etc. So remembering back to S1, we did this times this, plus this times this, plus this times this. So we did each x times its probability of happening. X times probability, x times probability, then we added them all up, and we added them all up. Now the difference between a discrete random variable from S1 and the Poisson distribution is that there isn't a finite number of values that x can take. It just goes on and on and on. So there's no way that we can just keep doing that thing of this times this, plus this times this, plus this times this, plus this times this forever, because we'll never stop. But we can write down what it would be, at least the first few terms. So the expectation of x would be, we've got this one times its probability. Well, that's easy, 0 times anything is 0. Then we've got this one times its probability. I'll just remind you of what the formula is for the probability. It's e to the minus lambda, lambda to the x over x factorial. Okay, so we've got x times the probability of x happening, which is going to be x, 1, times the probability, e to the minus lambda, lambda to the 1 over 1 factorial. Okay, plus, now 2 times the probability that it's 2, e to the minus lambda, lambda to the 2 over 2 factorial, plus 3 times the probability that it's 3, e to the minus lambda, lambda to the 3 over 3 factorial, plus 4 times the probability it's 4, e to the minus lambda, lambda to the 4 over 4 factorial. Wonder if I can squish 5 in. Plus 5 e to the minus lambda, lambda to the, oh that's not a very good lambda, lambda to the 5 over 5 factorial plus forever. Now the first thing we can see is that we've got an e to the minus lambda in every single term. So to simplify matters, we could pull that out the front. E to the minus lambda is going to help a little bit at least, and then let's have a look what we get inside. We get lambda over 1 factorial plus 2 times lambda squared over 2 factorial plus 3 times lambda cubed over 3 factorial plus 4 times lambda to the 4 over 4 factorial plus 5 times lambda to the 5 over 5 factorial plus forever and ever and ever. Okay, now I can do a little sneaky bit of simplifying. Have a look at these factorials on the bottom. This means 1 times 2. So I've got 2 on the top and 2 times 1 on the bottom. So what I can do is cancel that 2 and change this to 1 factorial. Here I've got 3, and then here 3 times 2 times 1. So if I cancel that 3 with the 3 in this factorial, then it will have a 2 factorial at the bottom, 1 times 2. Similarly here at the moment I've got 1 times 2 times 3 times 4 on the bottom and 4 on the top. So if I cancel that 4, this will be 3 factorial. And similarly, I can do this. Okay. Next step, pull out a lambda, because we've got a common factor of lambda here. Well, we've actually got, yeah, every single term's got at least one lambda in. So I'm going to pull out a lambda and just tidy it up a little bit. E of x equals lambda, e to the minus lambda. Then we've got 1, well, 1, because 1 factorial is 1, plus lambda over 1 factorial, plus lambda squared over 2 factorial, plus lambda cubed over 3 factorial, plus lambda to the 4 over 4 factorial, plus la 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 la. But, wait a minute. This here, that I've just written, is identical to what's written at the top of the page. Can you see that? This thing here is identical to this thing here, except for one difference. Fairly obvious, spot the difference. Down here I've got lambdas, up here I've got x's. So this thing here that I've got there is actually e to the lambda. How cool is that? Lambda, e to the minus lambda, e to the lambda, they cancel and we get the mean is lambda. And now the variance. We know from discrete random variables in S1 that the variance of a discrete random variable is the expectation of x squared minus the expectation of x squared. Now, you might just think, okay, I can see how this is going to go. It's going to go the same as we just did in the last proof, the proof of the mean. But I tell you what's going to happen is that it won't be as nice. It just goes horribly, disgustingly wrong. And some clever mathematician at some point realised that if you don't start by trying to calculate e of x squared, if instead you start with calculating this, then it's all going to work out beautifully. Okay, that sounds weird, but just bear with me, it's going to be okay. So here's our infinitely long table of different values that x could take, and what I'm going to do is just add another row along the top that represents x times x minus 1, because ultimately what I'm going to do here is the mean of x times x minus 1, not the mean of x. So I don't want this. So let's put that on the top. Okay, if x is 0, then x minus 1 is 0. If x is 1, then x times x minus 1 is also 0. And if x is 2, then 2 times 1 is 2. If x is 3, 3 times 2 is 6. X is 4, 4 times 3 is 12. If x is 5, 5 times 4 is 20. If x is 6, 6 times 5 is 30. And obviously in general, I've got x minus 1. So now we're just going to ignore this row and find the mean of x minus 1. So the mean in the usual way, this times this, plus this times this, plus this times this, plus this times this, plus this, la 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 forever. Okay, so here we go. We're going to do this one times this probability plus this one times this probability, and so on and so forth. So we get 0 for the first two, won't bother writing them down. Then we've got 2 times e to the minus lambda, lambda to the 2 over 2 factorial, plus 6 times e to the minus lambda, lambda to the 3 over 3 factorial, plus 12 times e to the minus lambda, lambda to the, 3 over 3 factorial, plus 20 times e to the minus lambda, lambda to the 4 over 4 factorial. I think that's all I've got room for. Okay, same as before, I'm going to pull out e to the minus lambda, because I've got that common factor in every single term. We'll have that e to the minus lambda in. E to the minus lambda. Okay, now what have I got? 2 lambda squared over 2 factorial, plus 6 lambda cubed over 3 factorial, plus 12 lambda, wait, what did I do? 12, look what I did there. 12 goes with 4. That probability is wrong. Apologies. That should be lambda to the 4 over 4 factorial, and this one should be lambda to the 5 over 5 factorial. I wonder how many people spotted that. Lambda to the 4 over 4 factorial plus 20 lambda to the 5 over 5 factorial plus la 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 la. Okay, let's pull out a lambda squared and then see what we've got. 2 over 2 factorial plus 6 lambda over 3 factorial plus 12 lambda squared over 4 factorial plus 20 lambda cubed over 5 factorial. Now these factorials aren't going to cancel quite as simply as the other one, but we can still do something with them. So for example, well, the first one's 1. This one's just 1, that's fine. But the other ones, so on the bottom here, we've got 3 times 2 times 1, and here we've got 3 times 2. So the 3 times 2 cancels the 3 times 2, leaving just a 1. Okay, next term. On the bottom here, 1 times 2 times 3 times 4. On the top here, 3 times 4. So these 3 times 4 cancel with these 3 times 4, just leaving a 1 times 2 on the bottom. And I think you can probably see where this is going. Here we've got 1 times 2 times 3 times 4 times 5, and here we've got 4 times 5. So those last two terms, well, last two, first two, depending on which way you think of it, are going to cancel with this on the top, leaving this, but a factorial, but 2 lower than it was before. So 1 over 3 factorial lambda cubed plus la la la. And you will recognise the big thing in the square brackets as being e to the lambda. Oops, I don't know why I put that in. So we've got lambda squared e to the minus lambda times e to the lambda. That cancels that, and we get lambda squared. Hooray! So what have we actually done here? We know that e of x minus 1 is lambda squared. But e of x minus 1 is the same as e of x squared minus x, just by expanding out those brackets. And we know from S1, that when you're doing e of two things, so for example e of x times by a add on b, that will just be the original e of x times by a add on b. So we can use the same rule here. This will equal e of x squared minus e of x, and that equals lambda squared. Okay, now we know what e of x is. E of x is lambda. We worked that out just now. So e of x squared equals lambda squared plus lambda. Okay, what next? Very, very nearly done. Look at our formula for variance of x. Okay, the variance of x is equal to the expected value of x squared minus the expected value of x squared, which is equal to, well, it's equal to this bit over here, lambda squared plus lambda, minus, and then e of x is lambda, which is squared. That cancels with that, and we get lambda.